sections, and I think we have a few examples we can practice. And so maybe let us work on that side. So if you wouldn't have the slides being printed, maybe I can rewrite here. So basically here we have the simple single degree vibrations. Okay, that vibration is associated with a machine kind of in rotating, say, engine. Okay, engine mount on some kind of truss. And that using the single beam, cantilever beam as the approximations. So basically for this case, you can imagine your system can be simplified by, for example, that equivalent spring constant of the strut, okay, or the beam. And then map with the mass. The mass can be the machine itself. So that's the K, this is N. And under this case, it's under the oscillating externally applied force, and that force basically is produced by the repeated motion of the piston. Okay, and if you will be able to, then we can formulate the force being transmitted produced by the piston is such that like 50 and say cosine 62.83 2t. Okay. So basically this one, like this. And now for this case, we simply put into informations, and we want to know is what we want to know. We want to find is the amplitude of the vibrations. So basically this problem is the single degree freedoms, and here we assume there's no damping. Okay, so for this case, even we don't consider the initial conditions because here he didn't provide the initial conditions. So we can gradually kick in the information piece by piece. So from here, our xt, the total response, and assuming initial conditions equal to 0, then basically that is a steady state response. And sometimes, if you like, you can simply using the SS, okay? The SS, that means steady state. And what is that? And from our equations, and if you remember, let me back to the few pages earlier. Okay, so either you like to pick this equation 1 or equation 2. And from here, equation 2, basically the first two terms, because of the 0 initial condition, the first two terms will be disappear. Only have the third term there. Okay, so we have the third term, then let me pick up that information for let me think about this one. here I come to myself a little bit kind of in kind of dilemmas. Okay, so by following up the thinking I mentioned to you, this is a total response, and the total response, and including the influence from the initial conditions, and also from the force excitation that combined in this term. Right now we don't have initial conditions. That means x0, this term equal to 0, and this term equal to 0, and leaving this term. Okay, so let me write out that term here. Okay. So for this case, it's saying the amplitude this one, I will go have that equation. Let me use I forgot that equations. Right now, I want to simplify this term. Okay, this term, let me utilize the equation that is cosine A minus cosine B equal to 2 times sine B plus A divided by 2 times sine B minus A divided by 2. Okay, so from here, before I plug in the amplitude, this term should be equal to 2 times f0, 1 minus omega n squared times sine, and omega n plus omega divided by 2t times sine omega n minus omega n divided by 2t. Okay, so this is a sine function. This is a sine function. Multiplied together, they will compose into new sine functions. Okay, and this is square. Under this case, I would say the amplitude should be equal to this term. Okay. This question is produced, I copied from our textbook. Okay, so under these situations, then we can calculate, so therefore the amplitude equal to 2f0 or f0 divided by k. Sorry, here I forgot this one. Okay, so I forgot that one. So that is f0 divided by k, and 1 minus omega n squared. And again, if you like to using the different symbols, like the 2 delta st and divided by 1 minus r squared. So from here, we can utilize the informations. So here the k, so let me say that here. So where the k is the our equivalent spring constant, for this cantilever beam, not cantilever, the both kind of constraint side beam, we have the K can be calculated by 192 EI and L cubed. That equation I got it from the mechanical material. Okay, and then we are given the Young's modulus, right? Where are we given the Young's modulus? So here I forgot to give you this one. So for the beam, we have the EI, E equal to 30 times 10 to the 6 psi. That's the given informations. And I equal to 0.2083 each to the fourth power. So that's the information and we are given. So we plug into here the K equal to 1200 pounds per inch. Okay, and then for this case we have the M. M can be determined by where 150 pounds of the weight. So divide weight by gravity constant, and this is a pound inch unit. So that is equal to weight divided by gravity. Okay, G is a gravity constant. So that is 150. And divided by 386.4 inch square per inch per second square. So that is, I just stop there. I don't implement that the information. So right now from here we want to know is what is delta ST. Delta ST equal to F now divided by K. So we also need to know F now, and F now is the magnitude of our given loading, and which is 50 pounds. Sorry, this one is in pounds. Okay. So we have F and we have K, so we can calculate delta ST. And also we need to know R. So R equal to omega divided by omega n. And what is omega? And omega is our working frequencies, and that is given by this number. That is omega. 62.832 radian per second. Okay, what is omega n? Omega n is our undamped natural frequencies K over m. So we already have K, we have m, so we can determine omega n. Okay, so omega n, which I simply leave there. So by doing this, then we can proceed these calculations, and the calculation from this one is minus 0.3008, and that is in inch. The minus appears because R squared is greater than 1. Okay, here I will make another note to you. Okay, so I wait for you to finish the writing here before I'm making that note. So the note I want to make is this. This is our the curve, and this one is for 1 divided by 1 minus R squared. And from this curve we can see that basically it's occupied the positive Y value or negative Y value. And right now for our case, the working frequency simply is such that R is greater than 1. So under that case, we expect the calculation result for this multiplication factor is negative. Okay. And mag is a negative basically with combining multiplication of this term basically give us the amplitude. And here the calculated amplitude naturally, if we do make no mistake, it comes with a negative. Sometimes it's very ambiguous. We know that for any oscillations, the amplitude defined as from peak to 0, So in my personal understanding, the amplitude should be always a positive number because we describe it as a quantity. It's a positive quantity, right? So I would say sometimes the minus we can put into phase. So let me explain this one. You can imagine if we have spring and the mass is here. So say you could imagine this spring is very hard, okay? Then I don't have that kind of the teaching aid, but I need everyone to imagine. So if I will hold this mass and using my hand as the to drive the externally excitations. So now I try to oscillate this system very slow. Okay, so once the system gets into its equilibrium, basically the system will move along with my hand, right? Okay, and that is called the in phase. In phase, that means the external force, my hand, moving in one direction, this mass will move in the same direction. That's called the in phase. On the other side, if I try to move the things very quick, then in that situations, the system's movement will be in the way that the degree of freedom, the xt, will move into the opposite directions of that force, the directions. So for that case, we call it out of phase, or the phase angle simply is 180 degrees, and that appears in this such a negative term here. Okay, so so that is a note I want to make, and in such a way, in the homework exercise, I think in one question I forgot the problem 4, problem 5. And you should expect the calculated amplitude to become negative, but I make a very long note at the end of the problem statement. I say usually the amplitude should be defined as a positive numbers. So if you would have any negative number, negative term, then you simply report is the magnitude only. And in that note, I explained again, the negative usually meaning the out of phase, so we put into the phase diagram, or yeah, so that is the note we taking here. And in the exam, I will try to be very specific. And so I would say either you give me the magnification factors. For magnification, the magnification factor that can be positive or negative. In this way, we don't have any ambiguity. Or otherwise, I would indicate you give me something. I'll be very specific. Okay. So that is a note here. And the second note I want to make is this. For us, we're leading to such the formulation, which means we have the multiplication of factor 2 here. And this problem is from our textbook. If you look at the textbook carefully, actually the textbook is the solution is easier. It's simply saying the steady state response is equal to capital X and multiply with cosine omega t. And here the capital X is equal to delta st and 1 minus r squared. This one is back to our very early the notes here. So we start from the beginning, okay? So that's where we've been through, and okay, if you remember our lectures last time, and we individually studied this form, in particular XP form, okay? And XP particular solutions are taken out this form. Okay, and that is an exercise from our textbook. The textbook simply directly put this one into calculation, and that one simply is 2 times off from our exercise here. Okay, so again, in my exercise, I would feel for these questions, because he didn't specify initial conditions, so we assume initial condition 0. And my personal feeling is this one will be more appropriate than the exercise by our textbook, because this makes more physical sense than this one. This one only exercise the steady state, the only exercise the particular solutions, okay, and just knock out no considerations from the initial conditions, and that one, well, okay. So here I propose the kind of the demonstrate two solutions thinking. This one from our textbook. This one, I will feel this is more complete, more appropriate. But here I leave the justification for you to think. Okay. So that is the then we can go to this one. How much time we have?